2015, even if we have very low cement production, cement still have contributed to up to 16% of CO2. So that's why we are here, and we hope that we can contribute something to at least lower down the CO2 emission from this industry. Okay, so this is why we need to look for alternatives. We have to tailor made our design, mix design to some application. Okay, so now we go into geopolymer and alkali activated materials. So what is geopolymer and alkali activated materials? Why do we have two names like this? When are we using geopolymer? When are you using alkali activated materials? So in general, it is using waste materials like fly ash, okay, or GGBS or slag, or we can also use some natural minerals. And some of these waste or byproducts from the industry, they have certain properties. They have been used. Okay, for example, fly ash has been used not only it has been used with cement. Okay, so we call it supplementary materials or mineral admixtures. Okay, but in this case, in our products or in our binder geopolymer or alkali activated materials, we we use it solely. We don't mix it with any cement. So we call that um, the first starting material, which is solid precursor, and we mix it some alkaline solution. Okay, so we found that when we mix them, there is some reactions. Okay, and they are hard. They become hardened and can be used for production of mortars and concrete. Okay, so when does this started? Okay, so actually the use of geopolymer or AAM, it started way back. Probably the first investigation on it is by Purdon in the 1940s, where he used slag, okay, to with sodium hydroxide. So you can see that there's some liberation of silica, alumina, and lime from minerals and glasses in sodium hydroxide. So this is a thing in now Ukraine, where this was the first precursor that started as and what we call alkali activated materials. And you can see that there is, he observed there is a formation of hydration of calcium silicates, which is similar to what we've seen in OPC, right? Where we have calcium silicate hydrates, and then there are some aluminates because slag also have some alumina, which we'll look into that. And regeneration of caustic solution, meaning the binder that he produced is also very highly alkaline, just like what cement binder would do. Then Gutkovsky in the 50s also did something similar with other minerals and also identified CSH in the system and some calcium and aluminum silicate hydrate as solidification products on the alkali activation of slag binders. And clay minerals react during alkali treatment to form aluminum silicate hydrate. So also as a hardened binder and very similar to the structure of CSH in cement binder. And of course, we can say we can give our credit to Geopolymer, to Davidovitz, who has started in the 1970s throughout even until today on using other minerals. In this case, it focused on a very high silicate and high aluminate content, such as metakaolin or kaolinite, and mix it with some hydroxide and silicate to produce a 3D cross-link polysilicate chain, which is basically like a SiO4, Si alumina silicate and silicate oxide, which resulted in a very it's a polycondensation reaction. So he used a lot of minerals such as clay, slag, fly ash, and so on, And also in the 90s, he also used NMR to analyze that in these materials, show that there is a uptake of alumina in the gel. Okay, so these are the earliest works, and of course there are tons of other works, including you guys who are doing this, right? So one of you here would be part of history to produce something that can benefit to other applications, right? So this is just the backstory of how geopolymer and alkali activated materials come into the picture. And then the latest will probably be the works of John Provis, Australian team, and Colombian team, a lot of teams, right? China as well, who then look into details of how actually these materials, okay, such as fly ash and others, especially with high alumina and silicate content, start to looking into how they behave, how they react, okay, and what will be the products at the end product of the binding gel. So this is like an illustration from Provis in 2005, who illustrate the reaction process of geopolymer binders. This is, I believe, high high silicate and alumina content, and mixed with silicate or hydroxide, and you take all the species from the aluminosilicate sources, will dissolve, and then they rearrange themselves, okay, with the sodium that or silicate that's provided, and we'll have a kind of like a 3D network of geopolymeric binder. Okay, so this is like silicate and aluminate rearrange themselves to become a hardened binder. So this is like the basic illustration of how geopolymer binder mechanism. Okay, when you have aluminate silicate source mixed with the solution. So then we have this question. So what controls the properties of geopolymer or AAM? So there's a lot of sciences that we can explore. Of course, when we do PhD, we can't do everything here, right? We focus on some aspect, and then we focus on that. And then every one of us contribute to all the little concept or little factors that can contribute to what is the aim, which is to have a very a good mechanical properties, engineering properties, and eventually a durable concrete. But inside, behind the scene, well, I say behind the scene, is all the understanding the role of binder phase, the role of inclusion, the chemistry, the water content, the physics, okay, the metals, the alkali metals, the solution, and all these, right, contribute to our knowledge to before we can really use the product with confidence. So I'm not sure. I mean, all of us doing a lot of things, right? So we have to bear in mind. I want to implore that it's not just it's not just testing one property. You take one and understand what is going on with that one factor to give the whole picture of how AAM or geopolymer works. Okay, so I want to start with precursor selection or the starting materials. Okay, so I'm focusing today on the slags and fly ash. So during my PhD, I used both of these materials. So I'm sure by now, okay, you know what is metallurgical slags. Slags are byproduct of iron manufacture. Molten slag from the blast furnace is rapidly cooled and dried to form a granulate. So slag or blast furnace slag is excellent. It has excellent cementitious properties, meaning it has high calcium. Okay, so that is similar to the cement one. Okay, and when you mix with combined with Portland cement, it is very cementitious. Okay, it can give us the CSH binder. Okay, it's very fine. The fineness can be similar to Portland cement, and you can have poor crystalline phases with composition of um, 2CaO. So this is calcium aluminate silicate, calcium magnesium oxide silicate, and calcium silicate glasses. So it's very amorphous, so it's easy to react. So also because of its composition that is close to Portland cement, it is an excellent material for to be used. Okay, and of course, fly ash. I think all of us is very familiar with fly ash. It's generated during the combustion of coal for energy production. You have the byproduct or the waste. So there's a lot of studies. They also use the fly ash that is precipitate above the chimney or bottom ash that's collected down the chimney. So there's of course, this material, we don't want to waste it. I mean, we can't use it. They will dump it. So why not we use it? And this fly ash, okay, there are two types. One is with high silicate content, or low calcium content, or high calcium content. So in Sarawak, what we found that our fly ash is low in calcium. So in general, fly ash, it has a good pozzolanic properties, which means it's high in silica and very siliceous, give you siliceous product, or siliceous and aluminous product. So this property is good. So if you mix it with just cement, it can give you liberate some of the silicate and aluminate to give you secondary products, and also can also help with others, such as workability, give you a more compact structure or compact products. Okay, so it is very fine, powdery particles, mostly spherical in shape and glassy in nature. Most widely used are low in calcium, which is class F. They are very high in silica and alumina, but they also comes with other impurities. So this is also something that we can talk about, the impurities. There have been papers about what does zinc do there, how does zinc affect. So those are others that maybe we can work together someday and discuss about those. What magnesium do there, but the contribution to reaction is from the alumina and the silicate. So if you look at the main compositions of all these precursors, so normal Portland cement would have very high calcium oxide, silica oxide. So these two, the calcium and silica oxide, this is the one that will contribute to the main binder, the calcium silicate hydrate, CSH. However, fly ash will have a very high in silica aluminate. This is just in general. Okay, so that will not, because of the very low calcium, it does not produce calcium silicate hydrate, but rather alumina silicate binder. Now, with slag, the content for the calcium oxide and silicate is slightly less than those of OPC. It does have some aluminate though. It's higher than OPC. And with this, they can produce what we call calcium aluminate silicate hydrate. So there's an inclusion of some aluminate in the main binder. So this one will give us, if you look under the XRD or you look under the microscope, you can see the incorporation of aluminate in the binder. And metakaolin, which we know is high in silicate and aluminate. This is the work of many researchers before, also similar to the main binder in the fly ash. Now, I like to show this in most of my slides, actually. A paper from Scrivener in 2011 that is the very foundation, the very understanding of how selection of precursor will affect the hydrated product. So on the left side here is the main composition. So I would say that the main composition, all of these, calcium oxide, silica oxide, alumina oxide. So it is plotted in this called ternary diagram, okay, whereby on this lower part here, calcium oxide is the highest. Imagine this is some arbitrary 100%, okay, calcium oxide, and at the apex here is the silica oxide, 100%, and on the right side here is the 100% alumina oxide. So when we do the XRF or the analysis on the composition, you can see that pure limestone, okay, would sit at very high calcium oxide content here. Okay, so like almost 100% calcium oxide. And Portland cement would have some values, some include some calcium oxide, as we've seen just now, some silicate, and some very little aluminate. And when you move away, when you move up, you can see slag is in between. Okay, they have some maybe 50%, 40% calcium oxide, some silicate, some aluminate, and so on. And for fly ash, you see that it is class F, very little, almost very little calcium, but on the high side, on the very high content of silica oxide, and aluminate. Okay, and metakaolin is very high in aluminate and silicate, and so on. So this is the starting point, okay, of our main precursor. And if you understand this, we're able to understand what happened when we mix them. So in this ternary diagram here on the right side is the product of when you mix these, right, with cement. It's still mixing this with cement, okay? So for example, in Portland cement, when you mix with water, so it gives you CSH, right? So you have a ratio of C over S, calcium over silicate ratio, that we know by now contributes a lot to strength. Okay, usually it's between 1.5 to 2. And then what about when you add slag? So it will have some CSH also, but a bit reduced in the ratio, and so on. So when you have aluminate in the system, you will have some ratio here, calcium aluminate silicate hydrate. There are also some secondary products, and cement will give you portlandite. That's the main product from Portland cement reaction. And fly ash, because of the alkali activate alumina and silicate, so you can have very high alumina and silicate inclusion in there. Sorry. So this is like, if you want to understand what is going on with your product, you should start with this kind of analysis. Okay, where is it in the ternary diagram? It not necessarily have to be calcium oxide here. Maybe your material is high in magnesium, you can put magnesium oxide here. So you can compare what happened after you mix it, after you blend it. Okay. So now, what is the influence of all these precursors to geopolymers or alkali activated material properties? So first we have to classify, because we've been talking about geopolymers / alkali activated materials. So there is classification of alkali activated materials. All of these are called alkali activated materials. They are differentiated by the calcium content. Okay, so increasing calcium content, for example, in normal OPC would have, somewhere here, you have a very high calcium content. but very low in alkali, very low in alumina. Now on this line here, on the x-axis here is the increasing alumina content. So alkali activated material is in between. It has some inclusion of calcium, some inclusion of silica and alumina. So geopolymers are very low calcium content. So in other words, geopolymer is a subset of alkali activated materials. So if your material is very low in calcium and very distinctive alumina and silica content, you can call it as geopolymers. But if you're using something that is high in calcium, you should call them as alkali activated materials. So it's not wrong to call it geopolymers as alkali activated materials. So these are the understanding that we developed in back then. Okay, I'm not sure now. Maybe Prof can explain if there is some changes in this understanding. Okay, but throughout my slides, I would use them interchangeably. But I hope you understand that my understanding of this is that geopolymers is a subset of alkali activated material, and this is also all depend on the depend on the content of calcium. So again, now we are talking about when you have a mix of of slag and fly ash. For example, this is from another paper. The same ternary diagram. Okay, calcium here, aluminate here, and silicate here. And if you look at this, okay, the first sample is 100% slag, so it sits somewhere here. Okay, so that is regions of, so it is already separated by some regions. So here, if you don't have so much inclusion of alumina and silicate, you can say it should be region of CSH lah here. Okay, it's supposed to be region of CSH, not CASH. So CSH, calcium silicate hydrate. Okay, but in alkali activated materials or geopolymer, it changes. It depends on how much calcium is in your system, right? So for example, in this case, in this big circle in the middle here, this is regions of CASH, calcium aluminate silicate hydrate, and some it overlap with the sodium aluminate silicate hydrate. This is the condition where you probably will mix both of those materials. You mix slag and fly ash. So if you do the analysis, the EDX analysis, you can find that it sits here. So you know immediately, oh, I have a mix of alumina and silicate in my binder. If your materials analysis occur a lot of in this region, so we know that that is the region of pure sodium alumina silicate hydrate. Most of the time, a metakaolin will appear here, and very, very low calcium fly ash. So you appear here. Okay, so this is calcium and aluminate and silicate ternary diagram for alkali activated binders in general. Okay, so now how does this affect the structure of our microstructure, right? So they all go through the same process in the beginning, whereby it is dissolution of your precursor. Say this is your fly ash, for example, okay, and you have a lot of silicate, aluminate content, okay, and these are all your activators, species in activators, for example, sodium, silicate, and others, okay, and it will dissolve, okay, and then they go through rearrangement and exchange of the molecule bond and so on, and then they start to have some nucleation of the gel. This is the gel that is important for the strength, for the durability properties. Okay, It's similar to what happened when you have water and cement. Now, for binders that is low in calcium, you would have this sodium aluminate silicate hydrate. Actually, it is not supposed to have a hydrate term there because you don't really have water in the system. Because the activator here is, in this case, we assume that it is a pure solution, okay, activator solution, which we'll talk about in the activator slide later on. So you have aluminum silicate gel. Now this gel is different from very different from the uh, calcium based ones. Okay, so understanding our starting material content will then allow us to understand our products, and then we can analyze how is this going to affect your properties. How about when you have high calcium in your binder, in your starting materials, for example, in slag system, goes through the same thing, okay, except now there is a in the high calcium system, you can also look at the function of magnesium, okay. This paper by Provis and Bernal, where they found that there is some zeolites, okay, where when you have low magnesium content, you have some crystalline zeolite. So this next part here, okay, is secondary products, okay. And if you have high calcium content, you can also have other secondary products, and plus with the main binder. In this case, the calcium aluminate silicate hydrate gel. Now, this gel is also well understood already. This is similar concept to calcium silicate hydrate gel, but with very low calcium silicate, with lower calcium silicate ratio compared to OPC, some aluminum inclusion, and they have a lot of other secondary products. Now, this system is unique because we should not just depend on the calcium aluminate silicate hydrate gel alone. The secondary products like this can also affect your properties. Okay, but I did not look into this. Maybe you guys can look into it. Okay, for our next project. Okay. So, but this is understood. It is in this paper, and I know that John Provis and Susan Bernal are looking into this inclusion of these secondary products, how they behave. And then, of course, when you have a hybrid with or blended binder, which means you mix, for example, fly ash and slag together, and you can come up with both type of gel in the system. This is where, when we look under the ternary diagram, they coexist here in the system here. Okay, so so basically, they go through the same thing. It's all because of this. What we say is that the starting material, your mineral composition, will affect underneath. Okay, and therefore will definitely influence the behavior of your binder. Now, this is also another publication comparing most common reaction products in OPC and AAM. So we know that. So now we're starting to understand it's not just primary products. You can also have secondary products. You can look at this product if you're doing it under the XRD. You can see some hydrothalcides. So for high calcium binder, you will see some hydrothalcide and others. Okay. For Nash gel type, you will see all these zeolites. Okay. So let's try to move into, okay, so we sort of understand the primary ones. Does the secondary ones influence our properties, the properties of our material? So this is also has been published and also in the literature, and it's interesting to look into. Now, does precursor starting materials affect mechanical strength? Yes, absolutely. from this paper from Zoo 2019. Influence of precursor definitely have influence on strength. So these are, you can find this in literature for in general, low calcium series. Okay, low calcium binder have lower strength compared to high calcium ones. So of course, some of them are intermixed in between. Of course, it all depends on a lot of other things. For example, the quality of your starting material. So we can assume that the low calcium ones are like from fly ash and so on, and the high calcium ones is from slag. And there's also other material. If you are looking at other materials, you may want to compare with these as well. So yes, precursor, starting material, its composition has direct influence on strength. Now, this is something that we did at University of Melbourne. The microstructural characterization is not just on the EDX analysis. We've proven that, yes, these are high calcium system from the slag, and we compare it with the low calcium system. It's obvious that they are different in the binding nature. And when you use both, you can have a lot of range in between here. Okay, so EDX elemental plot is I would say very useful to see your reaction products, and then from there you can see something more. Under the microscope, on the micrographs of the SEM micrographs of the AAM that we use, also we can see the slag ones is looking similar like the ones in OPC. Okay, you can see some unreacted or partially reacted slag, very dense, and it really give good mechanical properties. When we have a mix of slag and fly ash, it is intermixed. It's coexisting together. Some are Nash, some are cash gels, and it also have some good mechanical properties. For the Nash gel here, it does also have lots of good mechanical properties. It's comparable. I can see the circular round shaped ones here. Those are fly ash, and some are already reacted, and lots of gels. What we see here is lots of binding gel. Okay, so we can't talk about strength if we don't talk about durability. So in this slide today, I want to share about the durability under two conditions. First is chloride. So this is like the mechanism of chloride attack. So chloride attack on your binder. If you have a very bad concrete, you will have cracking and spalling over the concrete cover, and then it will react with your reinforcing steel and make corrosion. So basically what we're saying is that your product or your concrete should be able to be very well made, okay, and able to resist the ingress of chloride or any other corrosive species to your reinforcing steel. We want to protect our rebar or steel reinforcement. So there are a lot of technique to test for durability in chloride. The one that I use is according to NT Build 429. It is a chloride migration. It is accelerated test. You have your chloride solution here, and you put your concrete sample here, and you turn on the potential here, give it some current, and we force all this chloride to go inside your concrete. And then we will split it and then we spray with silver nitrate. Silver nitrate will be bright, will show, if there is chloride, the silver nitrate will show bright precipitation. So this is also a good experimental setup, but it is an accelerated test. Okay, so how does precursor affect the chloride, the durability in chloride? So here is the section, the concrete section that we already cut after the experiment. And we can see that the slag, in the slag system, the precipitation is only up of chloride, or ingress of chloride is about 1 mm, okay, from the surface. As compared to OPC, which is very deep, up to 25 mm. So we can see that the the influence of slag, okay, and influence of our precursor towards durability. This bottom one is 50% slag, 50% fly ash. So this system have more correct penetration. Okay, so yes, precursor influence the durability. In this case, we're talking about chloride. Okay, so increase of chloride diffusion or migration with fly ash inclusion. Yes, we can also see that with fly ash inclusion, there is more chloride ingress. Okay, but in general, AAM perform better in this test than OPC concrete. There's another durability that we can test. We can talk about is the sulfate attack. Okay, so it is a complex process. It's chemical. It's also physical interaction. So sulfate usually found in groundwater, soil, industrial waste, or agricultural soil. Okay, so we know that OPC, if under very high sulfate environment, it can cause crack, spalling, expansion, and loss of strength. And then what happens is that there will be formation of sulfate bearing phases. So basically, the cement, the calcium will, the concrete will lose its calcium by the exchange of cation and ion, okay, with the cement. And with the reaction will give you brucite, gypsums, which is very expansive, okay, and will be bad for your concrete. So previous study shows that alkali activated slag did not expand, did not show any formation of all these expansive products. Okay, so fly ash show less visible deterioration compared to OPC. So this is just a case study where we study the effect of sulfate environment. In this study, we studied the cation, sodium sulfate, and magnesium sulfate. This is the sample of geopolymer, fly ash geopolymer. I think, sorry, this is a mix of 50-50. 50% slag and 50% fly ash. And we see that under sodium sulfate, the paste looks good. There's no deterioration whatsoever. This exposure in sodium sulfate that does not, when we studied under the ACM or XRD, there's no change in the minerals or binding phases in these samples. But if we expose it under the magnesium sulfate, we see a lot of secondary products. We see expansion, we see cracking. So what is the difference between this is the cation of the sulfate solution. So the key factor in determining the rate and effects of sulfate attack in the alkali activated binder system is actually the nature of the cation, which accompanies the sulfate and ion. So in other words, magnesium sulfate is more detrimental than sodium sulfate. And this goes to the how do you say, the content in the system, which is the calcium. So like OPC, we don't, magnesium will overtake the calcium, right, and become calcium sulfate or adam or brucite. These are very expensive um, um, crystals. Okay, and they will expand, and they will break your gel or your binding properties. And what happens is all the calcium will leach out. Okay, you in the beginning you have the calcium aluminate silicate hydrate, so the calcium will leach out and replace with magnesium. So understanding this is also important, so that we know if we want to use these materials, we want to probably check, is it the sulfate, is it the soil, for example, is the soil high in magnesium sulfate or sodium sulfate. So next, let's go to alkali activating solutions, one of the key ingredients in our AAM. So the most common ones would be alkali hydroxides, alkalines, whether it's sodium hydroxide, potassium hydroxides, silicates, and weak acid salts like carbonates. Okay, and these are probably well studied. Okay, I did not use carbonate yet. I'm intent to try with carbonate. Have you ever test with carbonate system? Anybody know? So it's interesting to see. So these are the normal ones. So of course the most popular ones are hydroxides. Okay, and I believe you can find this a lot in the literature. Okay, sodium hydroxide, potassium hydroxide. It depends on the concentration or the molarity. So you can use this with low calcium precursor. Curing, you may when you use hydroxide, you may need thermal curing. Some of the advantages we see in fly ash system is that it is excellent in heat resistance. So just like ceramics. However, this disadvantages is high permeability. And then silicates is also widely used. You can use it at lower concentration when you have higher calcium precursor. You can ambient cure this. Low permeability, but it is also high in viscosity. When you have a high viscosity solution, it's quite hard to work with, and it will can affect the reaction or the development of early strength or early reaction. So how does all this how does alkali activating solution influence again our strength, durability, and so on? So this is paper from Sheila et al. So he studied effect of molarity on effect of activator on strength. So it seems that if I'm not mistaken, this is sodium hydroxide. Okay, at day 7, his systems is good. The most optimum would be somewhere 14 to 16 mole. Okay, so definitely we can see the effect of activator on strength. Molarity of the activator. And what do you see under the microscope? So this is the case for Australian fly ash, whereby when they use NaOH, sodium hydroxide, it's very brittle and compared to when they use silicate. This is probably not the case for you. It all depends on, again, how reactive or how viscous is your starting material. So in this case, the fly ash does not respond well to sodium hydroxide, but good in silicate. And there's also when you adjust with the silicate ratio in your activator. This is the case of when you use metacolite. You can see that the solution ratio silicate to sodium solution. Okay, okay, will increase, will affect the compressive strength. And under the microscope, also see a denser structure uh, when you have certain amount of silicate. So this is more on controlling the silicate content of your activating solution. Now, this is also one of our works in UniMAP. This is a mix of a lot of mixes, molarity, water binder, some use silicates, hydroxide, and mix. This highest, so our fly ash at UniMAP is not very, it's not, I won't say it's not very, how do you say, viscous. You don't have so many, under the XRD that we don't see, it's not too glassy. So we have a problem with activating it. Okay. But when we put some silicate in our sodium hydroxide, we get a comparable compressive strength. Of course, this is on this is on concrete samples, and we're still studying it on how we can improve the strength. The lowest strength here, like 3 megapascal, is probably very high water binder. So these are all the accumulation of a lot of results. Currently, my PhD and my master's students are looking into all types of mixes as a function of molarity, as a function of water binder, function of activator types. This is how activator influence chloride penetration. You see that the 12 mole of sodium hydroxide give lower chloride penetration. This is also the case of locally available fly ash in Sarawak right now. So 25 mm penetration. This is also tested under the NORD test. I'm not satisfied, to be honest. So we have to readjust a lot of things to get a better penetration chloride durability. Excuse me. Okay. So again, but the main thing that we want to say here is that molarity will also influence your strength and your chloride durability. Now, I want to highlight another type of mix, which is 1 part geopolymer. I think maybe UniMAP has started doing something like this, whereby, so in the first slide that I showed you just now, a geopolymer is mixed with fly ash and mixed with alkaline solution, right? So that process is actually quite hazardous, okay, because the solution is very corrosive, and if we want to bring solution, it's very hard to work on site, for example, or if you want to work with very large amount of concrete. So this is also quite current. I mean, I would say current. Probably the last 7-8 years. There's another type of mixing that we want to look at, which is 1 part geopolymer binder, 1 part geopolymer concrete, whereby you don't use solution. Instead, you use your alkali pellets. For example, if this is sodium hydroxide, you just mix it with your fly ash. So all these are dry, right? And then you put water afterwards, okay? Or you can mix fly ash with alkali pellets, and then you mix water to it, give it a good mix, and then put your gravel and sand. So this is interesting because now we have water in that. That is H2O. And how does 1 part geopolymer fare to 2 parts, right? So this is also something that we're looking into. I would like to also, maybe we can discuss further if any of you are doing this kind of technique. It's also been published by Lukanen in 2018. A very nice literature review on this technique. So this, if we use one part geopolymer in this technique, it is easier to mix on site. It is easier for manufacturer for any for precast structures and then things like that. So our work shows that in terms of porosity, so one part geopolymer gives lower permeability. This is volume of permeable void test and compared to two part. The value for two parts concrete. This is again our local fly ash with NaOH pellets. The two parts is mixed. I think this is 10 mole, 10 mole. Okay, and this is consistent to with other publication that we found. So fly ash geopolymer concrete, basically what we found is that the voids is around 7, 8, 9, 10%. But when we did a one part system, we found that the permeable voids or the porosity is much lower, almost half from the two parts. So this is a good indication that one part system is doable, is comparable, and can be applied. We also compared one part fly ash geopolymer system when it comes to its chloride penetration. Like you seen just now, our fly ash geopolymer has quite deep chloride penetration, but it is worse at two part, okay, compared to one part. This is also NaOH pellets, one part system. So something can be done again to study how do we lower the chloride penetration in the system. This is specifically for our fly ash in Sarawak. Maybe it works better for other fly ash in other parts of Malaysia or elsewhere. So lower chloride penetration in one part fly ash compared to the two parts concrete. So in summary, based on these two main ingredients, we need careful selection, okay, of what is your activator, what is your precursor, and then the reaction mechanism of different binder can be further studied, especially understanding the secondary products from the main binder. And when we understand our microstructure characteristics, we can then make our concrete for what its intended use. Okay, can be tailored design, and then microstructure is an important key aspect in designing. Microstructure is important to understand and in designing for mechanical and durability performance. So what is the progress now in alkali activated material? Just share some last slides here. So Davidovitz in 2015 published this from his institute, Geopolymer. You can adjust your starting material and your product here to what is the need of your industry. So it's not just for concrete, for construction industry. You can also do it for fire resistant, heat resistant, so composites, toolings for SPF aluminum, sealant industry, fire protection, and so on. So what we're doing right now is the low CO2 cement concretes, okay, and there are more other application, toxic waste and encapsulation, carbon capture, for example, is also being studied because they studied that this material, when you have a good mix, a good characterization in terms of its microstructure, it can absorb carbon dioxide. So that is really good application. And where is the progress now? This is if you use zero OPC, okay, the CO2 emission, this is from Van der Winter study, that Van der Winter has a product called eCrit, which use slag system and fly ash system with zero OPC, and they studied that the CO2 emission is lower than this OPC, 100% OPC. So it is an inspiration. It is motivation to how do you say contribute to the environment protection. And there's some news. You can see that Lafarge has started to use alkali activated concrete. Okay, back in 2020. If I'm not mistaken, they use slag system. You can read it on worldcement.com. And some Google News about low carbon cement and super material geopolymer cement replace energy intensive concrete. So it has been highlighted, and under a good how do you say people have been giving quite attention to these materials overseas. I'm not sure in Malaysia. Okay. And in terms of money, we understand industry is always about dollars and cents. So where is this industry? You can read about researchandmarkets.com. The money keep growing. In the 2019, it was about 6 billion. Now it's USD 40 billion. So there is a how do you say motivation for maybe Malaysia, for example, our industry, cement industry, come together to use geopolymer or color activated materials. We understand that for other application, if you don't need 50 megapascal for slab, for example, right? So you can use geopolymer for maybe for brick, for example. We can work it out. But overseas, this has captured a lot of attention, and with regards to the environmental protection as well. So with that, I hope I'm useful for this presentation, and I want to take this opportunity to thank all of the participants here, and especially to Prof. Mustafa, and then my students. I don't know if they're in here. I invited them, Nurul, Hayes, Jasper, and all my previous FYP students and current FYP students who work really hard. Yeah, that's all from me. Thank you.
So thank you very much to Dr. Idawati, binti Ismail, for a very interesting speech, very interesting sharing session this morning. It's very interested to know that how promising it is, this geopolymer, since from 6 to 40 billions now. So
Correct.
hopefully that will be like you said, like you mentioned, it will be, inshallah, will be a motivation for all researchers,
Mm-hmm.
industries, and it
Mm-hmm.
also shows how promising it is for the next research stages of everyone. Okay, now let's open any questions to the floor, to the participants. Uh, Please, you may ask directly to the speaker, Dr. Idawati, or you also may um, type it in the chat box. Anyone would like to ask any questions?
Tak ada.
Tak ada
No question.
so far.
Maybe they're doing more advanced than what I
Can
presented
I have
today.
can I talk to Dr. Indawati, please?
Yes, Prof.
Yeah,
Hello.
yeah. My name is Kannan from India. My interest is more on the clay brick industry, to bring in geopolymer for the clay brick industry. So I want to
For
know for the clay brick
what
industry,
industry? Sorry.
clay brick industry.
Oh, brick. Okay.
Yeah, yeah. The metakaolin.
Metabolic. Yes.
Yeah. Is there any limitation or requirement in terms of alumina silica ratio to have a very good geopolymer brick?
Okay. So I'll show you again the slides.
Yeah.
If you look at the works of Professor Davidovich here,
Yes.
right?
Yes.
He identified the type of silica alumina ratio for the purpose, for the intended purpose of your material. So if your clay bricks, probably here,
Yes.
or do
Yes.
you want it to be super high resistance, you can increase the silica alumina ratio. But basically it's 1 to 1, so just normal. But do you like a ceramic? What is your starting material? Or metacolonite, is it?
Yeah, metacolonite. Yeah.
Oh, okay. Yeah.
So I know if I in place of silica alumina ratio, supposing I give say percentage of alumina say is about 18 to 20%, and silica is about 50-60% in clay, and total coming around 70% of the total clay. Will that material be suitable to make geopolymer bricks?
How many percent? Sorry.
Say 15 to 20% of alumina and 50% of silica.
Oh, okay. Let's is it similar to this?
Yes. Yeah.
Yeah. So then,
Yeah,
yeah, it
alumina will
should
be
be good.
lower.
Yeah, it should be good.
Okay.
Have you tested it?
I did try some small samples very long back, and I could get about say 30 megapascal compression strength.
I think 30 is good.
Yeah, but the material was tearing. It was not breaking, but it was tearing.
Oh,
So I needed to make it more stronger, like a brick, and not tear like.
yes, yes.
Yeah. I think I was
So,
in touch with Mr. Mustafa sometime back regarding this, but that was a very small project I did when I was in Malaysia. This is
uh,
just for information. I thought maybe I can develop on this further.
we few years back ago, my student also did brick, but we did based on fly ash. But it did not tear.
Okay, okay.
Yeah, we did fly ash based bricks before. We got about 30 to 40 MPa as well. And it was good. It was behaving as a normal
Normal brick.
compressive and breaking mechanism. It does not tear.
Okay. Yeah, thank you very much, Doctor. It was very useful and very informative, especially for people like me who are not from the research background. We are more of a industrial background,
Ah,
manufacturing.
ah.
I'm also a ceramic engineer, so I could
Yes,
pick up
yes.
the basic of what you